Hi students, today we discuss about configuration of molecules, okay, in terms of relative configuration and absolute configuration, right? So relative configuration nothing but DL configuration and absolute configuration nothing but RS configuration, okay. So where we are giving RS configuration and where we are giving DL configuration, that we will see now. First of all, I am going to write this configuration of molecules. Configuration. So configuration we have two types. First one, relative configuration. Relative configuration. Relative configuration. Second one, absolute configuration. Okay. Absolute configuration. Relative configuration and absolute configuration. So absolute configuration nothing but RS configuration. Okay. Absolute configuration nothing but RS configuration. Next one, so relative configuration nothing but DL configuration. DL configuration. So what is the difference between these two and where we are applying this DL configuration and RS configuration? Now we will see now. First of all, come to that DL configuration. Now DL configuration comes under relative configuration. Now this one comes under relative configuration. Okay, relative configuration. So where we are applying the relative configuration. So DL configuration mainly we are applying on Fisher projections. So already we know that different types of molecular representations are molecular projections. Okay. So like wedge projections, Newman, Sahars, zigzag, Fisher, like that. So now from all these five different types of molecular representations, now DL configuration particularly we are applying on Fisher projections. Why? Because that DL configuration proposed by Fisher. Now DL configuration applied on Fisher projections. Okay, right. So actually here in case of Fisher projections we have sugars, sugars and amino acids, sugars and amino acids. Okay. So in case of sugars and amino acids, now we are going to write that DL configuration, right? First, basically, I want to tell one important point that so we have like DL configuration and small d, small l. So what is the difference between these two? So if you are using capital D and capital L, now capital D and capital L tells about the relative configuration. Okay, and what about small d and small l? Now that small d and small l terms comes under what? Now optical rotation, right? Now these two terms are related to optical rotation. Small d nothing but dextro-rotatory compound. Small d nothing but dextro-rotatory and small l nothing but levo-rotatory. So that is related to optical rotation. There is no relation between capital D, capital L and small l. There is no relation between D and small d, capital L and small l. These two are what completely different. Capital D and capital L nothing but relative configurations, small d and small l related to optical rotation, right? Now here we are talking about capital D and capital L configurations. So where we are applying that DL configuration. So DL configuration or relative configurations, now we are applying in sugars and amino acids, particularly on Fisher projections. Okay. Now in case of sugars, if you want to give DL configuration, now just to remember one reference molecule, that is glyceraldehyde. Glyceraldehyde molecule. This is our reference molecule to provide DL configuration. Next, in case of amino acids, serine, serine is the reference molecule. Sometimes, now these 2 points important for theoretical questions, you remember. Now in case of sugars, who is the reference molecule? Glyceraldehyde or D-glyceraldehyde. Okay, right. Next one, in case of amino acids, which is the reference molecule? Our reference molecule is serine. Okay, with the help of these two, we are giving DL configuration in sugars and amino acids. And you remember one important point, natural sugars and natural amino acids. Okay, very important point. Natural sugars, natural sugars having D configuration. Natural sugars are having D configuration. Next one, natural amino acids. Natural amino acids are having natural amino acids are having capital L configuration. Remember these 2 points. So first of all, in sugars, which is our reference molecule, glyceraldehyde is the reference molecule, okay. But in case of amino acids, which is the reference molecule, serine is the reference molecule. Here I am not going to write all the structures, that is separate chapter is there like biomolecules and amino acids, right. So there we will see all types of molecules. Just here you remember these 2 points. Natural sugars are having D configuration, natural amino acids are having what? Capital L configuration. And who is the reference molecule for sugars? Now in case of sugars, our reference molecule is glyceraldehyde, but in case of amino acids, who is our reference molecule? Our reference molecule is serine. Okay. Now first let me start from sugars. In case of sugars, now which is the reference molecule? Glyceraldehyde. I am going to write the structure CHO, CH2OH, next one here OH and H. Another molecule I am taking CHO, CH2OH, left side OH, right side hydrogen. Very simple to give relative configuration in terms of D configuration and L configuration. First of all, in case of sugars, now just you look at bottommost carbon atom. So here actually this is our bottommost carbon atom, right? At the bottommost carbon atom, in case of sugars, just we are looking towards OH. Okay, at bottommost carbon atom, how that OH is connected, right side or left side? This OH connected right side. And come to second molecule. Now in this molecule, same OH connected left side. That OH connected left side. Very simple. At bottommost carbon atom, if your OH is present right side, simple configuration is D configuration. And here at bottommost carbon atom, if same OH is connected left side, now that is what? L configuration. Okay, that's the thing. Whatever the number of carbon atoms present, like 3 carbons, 4 carbons, whatever the number of asymmetric centers, now we are looking towards only bottommost carbon atom. At bottommost carbon atom, if your OH right side, D configuration, and at bottommost carbon atom, OH left side, simple L configuration. And you remember this point also, if you want to provide DL configuration, to provide DL configuration, now Fisher should be in golden form. Fisher projection, Fisher projection should be taken in golden Fisher form. Golden Fisher form. What is the meaning of golden Fisher form? Already all types of rules are completed in the previous lecture. So if you want to write the Fisher projection or golden Fisher projection, first important point, maximum number of carbon atoms should be on the vertical line. Okay. And what we are taking at the top of the vertical line? At the top of the vertical line, we are using more oxidizable group. For example, here CHO and CH2OH groups are there. Okay. Which is more oxidizable group? CHO is more oxidizable group when compared to CH2OH. Okay, this is our golden Fisher form. Now these two are called as glyceraldehyde molecules. Now first one, D-glyceraldehyde, capital D. Okay, next one, this one capital L glyceraldehyde, capital D and capital L. Now I am going to take next molecule like this, CHO and CH2OH. Here both OH groups are given from right side, H and H. This is the molecule. Okay, right. For example, same molecule if they are giving like this, CHO and CH2OH. Now these two OH groups. One second. CHO and CH2OH. Here OH right side, hydrogen left side. Here OH left side and hydrogen right side. First of all, provide DL configuration. So to provide DL configuration, now which carbon atom is reference or bottommost carbon atom? This is the bottommost carbon atom, and here also bottommost carbon atom. At bottommost carbon atom, what is the orientation of OH? We don't want other OH. We don't want this OH and this OH. Just we are looking towards the OH which is connected at bottommost carbon atom. So if your OH right side, then what is the configuration? D configuration. and here also same thing, D configuration. Okay, and if you want to write in terms of erythros and threos, now according to erythros and threos nomenclature, if similar groups are present in same site, that's what we call erythros. Now this is also known as D erythros, D erythros, and this one is taken as D threos, D threos. If matching groups or similar groups are present in same site, that's what we call erythros, and similar groups are present in opposite direction, that's what we call threos. Okay, now this is the D threos molecule, and this one, sorry, D erythros molecule, and this one D threos molecule. Okay, fine. Next one, for example, if you are going to increase number of carbon atoms like this CHO and CH2OH, now OH groups are given like this: OH, OH, hydrogen, hydrogen, and hydrogen. Okay, right. Next one, if CHO and CH2OH, here OH right side, OH right side, here OH left side, hydrogen, hydrogen, and hydrogen. These are the two molecules given. So we don't want names of the molecules like arabinose, ribose, arabinose, xylose, lixose. Names not required. Now, how to give DL configuration for these molecules? Now, if you want to give DL configuration, just you look at bottommost carbon atom. We don't want remaining all the OH groups. Here also same thing, just you look at bottommost carbon atom. At bottommost carbon atom, what is the orientation of OH? Connected right side or left side? Right side. Then what is the configuration? D configuration. And here also same thing. Now that OH group is connected right side, again what is the relative configuration? Capital D. Okay, now this molecule is known as D ribose, D ribose, and this one D arabinose, D arabinose, like that. Ribose, arabinose, xylose, lixose, lot of molecules are there, but we don't want all these things. Just look at the Fischer projection in sugars, and at bottommost carbon atom, if your OH connected right side, then what is the configuration? D configuration. And if your OH is connected left side, L configuration. But naturally occurring sugars are having what kind of configuration? Capital D. And one more molecule I am giving, that CHO and CH2OH. Now this molecule we observe in biomolecules, and here OH, next one H, OH, and OH, hydrogen, hydrogen, OH, and hydrogen. Now this is the given molecule. Okay, fine. Here how many asymmetric centers are there? So we have 4 asymmetric centers, but whatever the number of asymmetric centers, in order to give DL configuration, just we are looking towards this carbon atom, bottommost carbon atom. At the bottommost carbon atom, your OH is connected to right side or left side. Your OH is connected to right side. Then what is the configuration? D configuration. Now this is known as D glucose molecule. D glucose molecule, right? So that is the way of giving DL configuration. Next one, for example, if molecule is given like this: CHO, CH2OH, left side OH, right side hydrogen, left side OH, right side hydrogen. So what is the configuration? Here for giving DL configuration, same thing, just you look at this bottommost carbon atom. What is OH connectivity? OH connected left side or right side? Your OH connected left side. Then what is the configuration? L configuration. Okay, so that is the way of giving DL configuration in sugars. Next one, come to what? Amino acids. DL configuration in amino acids. In amino acids, which is the reference molecule? So our reference molecule is serine. Okay, so there are naturally occurring amino acids, essential and non-essential amino acids, but right now we don't want all these things. Just you look at this molecule, only one example is sufficient. Now here CH3, for example, here NH2 given and hydrogen. Okay, and here I am going to take another molecule CH3. Here I am taking NH2 right side and hydrogen left side. Okay, so to provide DL configuration, just you look at this carbon atom, bottommost carbon atom. In case of amino acids, if your NH2 present right side, D configuration, and NH2 present left side, L configuration. What is the connectivity of NH2? Now that NH2 is connected to left side or right side. Here that NH2 connected to left side. What is the configuration? L configuration. Next one, if same NH2 connected to right side, then what is the configuration? D configuration. These examples are sufficient for relative configuration, that is capital D, capital L configuration. So once again, before leaving this DL configuration, so I want to repeat the same point, capital D and capital L. What is the meaning of capital D and capital L? These are the relative configurations, and where we are using these relative configurations only on Fisher projections. And what is the important condition? Your Fisher should be in golden Fisher form. Okay, right. And for sugars, what is the reference molecule? Glyceraldehyde. In case of amino acids, which is the reference molecule? Serine. In sugars, at bottommost carbon atom, OH right side, then what is the configuration? D. And OH left side, L. In amino acids, at bottommost carbon atom, if you are NH2 right side, what is the configuration? Capital D. And same NH2 left side, then what is the configuration? L. Okay, next one. Come to absolute configuration. Here, in case of absolute configuration, absolute configuration. Now this absolute configuration also known as RS configuration. Okay, RS configuration comes under absolute configuration. So what is the meaning of absolute configuration? So basically in case of DN configuration, whatever the number of asymmetric centers present, that DL configuration providing information about only at bottommost carbon atom. That is not going to tell about the another carbon atoms. But in case of absolute configuration, not like that. Whatever the number of asymmetric centers present in the given molecule, right? So that is providing information about all the asymmetric centers. That's why that configuration is known as absolute configuration. Okay. So now here, what is the meaning of R and S? Now R nothing but rectus, R nothing but rectus, and S nothing but sinister. Rectus and sinister. Rectus nothing but clockwise direction, sinister nothing but anti-clockwise direction. Okay, that is the meaning of R and S. So first of all, R and S either relative configuration or absolute configuration. Now this RS comes under absolute configuration. What is the meaning of R? Rectus, and C nothing but sinister. Rectus nothing but clockwise direction, and sinister nothing but anti-clockwise direction. Here the thing is, not like DL configuration. In case of DL, just we are looking towards the bottommost carbon atom and we are providing capital D and capital L. But in case of RS configuration, some rules are there. Okay, with the help of those rules, we are providing RS configuration. Those rules are known as CIP rules. With the help of CIP rules, we are giving RS configuration. What is the meaning of CIP? Three different people proposed these rules, CIP rules. C nothing but Khan, and I in gold, and Pralag. These three people proposed rules, CIP rules, Khan, Ingold, Pralag rules. Okay, these are known as simply CIP rules, Khan, Ingold, Pralag rules. So what are the CIP rules? One by one we will discuss about the CIP rules. Now first point, according to CIP rule, we are giving priorities 1, 2, 3, 4. Okay, 1, 2, 3, 4 priorities. So how we are providing those priorities? First point, directly we are going to atomic number. Okay, according to CIP rules, the first rule given that provide 1, 2, 3, 4 priorities on the basis of atomic number. Now I am writing same point. Now priorities are given on the basis of atomic numbers. On the basis of atomic numbers, that is the first point. Priorities are given on the basis of atomic numbers. Okay, now higher atomic number getting higher atomic number getting high priority or higher priority. That is the first important point. So whenever RS configuration given, absolute configuration, first we are going to atomic number according to CIP rules. According to CIP rules, how we are providing priorities? Priorities are provided on the basis of atomic number. Okay. First one, priorities are given on the basis of atomic numbers. Higher atomic number getting what? Higher priority. For example, here iodine, next one bromine, chlorine and fluorine given. Which one having higher atomic number? Iodine. Next bromine. So okay, this is the decreasing order of priorities. Decreasing order of priorities. Iodine, bromine, chlorine and fluorine. For example, if you want to give 1, 2, 3, 4 priorities, now first priority should be given to what? Iodine, and second priority given to bromine, third priority given to chlorine and fourth priority given to fluorine. Okay. So always higher atomic number getting what? High priority, and lower atomic number getting what? Lower priority. So among these, iodine first priority, bromine second priority, chlorine third priority and fluorine fourth priority, right? That is the first rule. Now come to second rule. For example, sometimes atomic numbers are same. According to the given group, sometimes you are getting same atomic number. For example, here hydrogen, deuterium and tritium. Hydrogen, deuterium and tritium. These are the isotopes. Now we can write like this: H11, H12 and H13. H12 also known as deuterium and this one is known as tritium. Okay. Now these three species atomic number same or different, same atomic number, fine, and mass numbers are different. For example, whenever this situation occurs, same atomic number but a different mass numbers, in that case we are giving high priority for high mass number. These are the priorities. Tritium higher priority than deuterium and deuterium higher priority than hydrogen. Okay, you write same point. If atomic numbers, but this situation particularly we are applying in isotopes. If isotopes given, then what is the situation? In case of isotopes only, if atomic numbers are same, then priorities are given on the basis of mass numbers. On the basis of mass number. This is the second important point. Okay. If atomic numbers are same, then go for mass number. So if you are giving priorities on the basis of mass number, how we are giving? Higher mass number getting what? High priority. So for example, hydrogen, deuterium and tritium are there. High priority given to what? So high priority given to tritium, first priority, and this one second priority, and hydrogen getting third priority. So that is the way of giving priorities on the basis of mass number. If isotopes are given, if atomic number is same, then do like this, right? For example, here groups are given like this. Now CH3, next one CD3 and CT3. CH3, CD3 and CT3. First of all, atomic numbers same or different? First we are looking for first connectivity, right? Now who is the first connectivity here? Carbon. Next one here, first connectivity carbon. Here also same thing, first connectivity carbon. So here atomic number same or different? Atomic number exactly same. Okay. On the basis of atomic number, now we are unable to provide that priorities 1, 2, 3, 4 priorities. Okay. In that case, we are looking towards the mass number. CH3, CD3 and CT3. Which one having higher mass number? CT3. So first priority given to what? First priority given to CT3, second priority given to CD3 and third priority given to CH3. Now this is the increasing order of priorities. Okay, that is the situation in case of isotopes. Clear? For example, if molecules are given like this, Now CH2 and CD3. Next one CH2 CD2 and CH3. Next one directly CD3. Next one CH2 and CD3. So what is the way of giving priorities? Now here four groups are what given. Just I am giving like this: A, B, one second. Okay, no problem. A, B, C and D. How we are giving priorities? First of all, here first connectivity point of view, atomic number of carbon same or different? Atomic number same. Next one, come to the second connectivity, atomic number same or different? Same atomic number. And there is a extension in one A, B and D. Sorry, in A and B. Now C molecule is going to stop here only. In case of D, that is going to stop at second carbon atom, but there is an extension in A and B. Now these are what extended up to 3 carbon atoms. Okay, that's why first you select priorities in A and B. So in A and B, here CD3 present, next one CT3 present, CH3 present, CD3 and CH3. Now which one getting high priority? High priority should be given to A. That is the priority order. Next priority given to what? B. Okay. Next one, in case of C and D, which one getting higher priority? Now in case of C, CD3 given, but here CH2 and CD3. There is a further extension in this carbon chain. Okay. Now here don't stop here. First you compare between CD3 and CT3. Again there is extension in case of D. Now you don't stop here. Now in case of D, there is another carbon atom. That's why priority should be given to what? D, and last priority given to C. So that is the way of giving priorities. Okay, right. Next one, for example, here OH given, next one OCH3 given, next OCH3, 18 isotope is given. Okay, what about the priorities according to the given groups? Now clearly I am writing like this: OH. Next one here OC, hydrogen, hydrogen and hydrogen. Next one OC, hydrogen, hydrogen and hydrogen, but here 18 isotope is given. Okay, right. Now in this one, now this is our first connectivity, oxygen, here also oxygen, next one oxygen. First connectivity I am writing like this. So which is the first connectivity? Oxygen, oxygen, here oxygen, but isotope is given 18. Okay, right. Next one, in between these two, if you compare between second group and third group, so definitely which one getting higher priority? Higher priority should be given to this one. What is the reason? Atomic numbers are same. Because of same atomic numbers, then we are going for mass numbers. Next one, in case of second connectivity, here hydrogen, but here carbon atom is present. So definitely which one getting higher priority? This group getting higher priority when compared to OH. That is the way of giving priorities. Now simply always, if same atomic numbers are present, then you go for mass numbers. Okay, right. Next one, for example, groups are given like this. Here 6-membered ring system. Next one 5-membered ring system, 4-membered ring system and 3-membered ring system. Now these are the given groups. How we are giving priorities for the given groups? Now free valence is nothing but these are maybe connected to what asymmetric center. Now you start from this first carbon atom. Here also same thing, first carbon atom. Okay. Here first connectivities are same. Then go for second connectivity. Okay, wherever you are getting first point of difference, then we can differentiate and we can give the priorities. Now in this one, now what is the degree of this carbon atom? 2 degree. Next one here also 2 degree. Next one 2 degree. Next one here also 2 degree. Okay, right. There is no point of difference. Why? Because all are 2 degree carbon atoms. Next one, go for another carbon atom for getting first point of difference 2 degree. Here also 2 degree. 2 degree carbon atom again. 2 degree carbon atom. Okay, right. Again we are getting same carbon atoms, there is no point of difference. And here 2 degree carbon, 2 degree carbon, 2 degree carbon, but what is the carbon atom here? 3 degree carbon atom. Just we are moving like this. Okay, so where you are getting 3 degree carbon atom, in the last one you are getting 3 degree carbon atom. That's why first priority should be given toward this one. Okay, next, how to decide among these three molecules? Again I am moving towards the another carbon atom, 2 degree carbon, 2 degree carbon, but here what we are getting? 3 degree carbon atom. Okay, next priority given to this one. So like that, if you are moving to next carbon atom, 2 degree carbon, but here 3 degree carbon atom. So third priority given to this one and fourth priority given to this one. Okay, that is a way of giving priorities. 3 degree carbon, nothing but what? That should be what? Connected to 3 carbon atoms. So 3 carbon atoms, 3 degree carbon, nothing but carbon which is connected to 3 carbon atoms. Okay, so in case of priorities, 3 degree carbon greater than 2 degree carbon greater than 1 degree carbon atom. Okay, so that is the way of giving priorities according to the given molecules, given groups. Okay, next one, I am trying to explain duplication and triplication. Another important point, duplication. What is duplication and what is triplication? Duplication and triplication, and where we are applying. Again same situation, sometimes we are unable to differentiate on the basis of atomic number, and there we are taking help from duplication and triplication. So where we are applying duplication? Duplication applied on double bonds, applied on double bonds. Triplication applied on triple bonds, triple bonds. Now these are applied on triple bonds. Applied on triple bonds. Okay, duplication applied on double bonds and triplication applied on triple bonds. Very easy to apply that duplication and triplication. Now first you start from like C double bond C, C double bond C. Just in order to differentiate, let it is first carbon and second carbon atom. Just for clear understanding purpose, I am taking C1 and C2. Okay, and how to apply duplication? If you are applying duplication, now in case of duplication, first of all, here there is a sigma and pi bond. One sigma and one pi bond is present. Okay, now in case of duplication process, first you break pi bond, break pi bond, but not sigma bond. Just we are breaking only pi bond. Okay, after breaking of pi bond, right, the valence is decreasing. After breaking of pi bond, simple, C2 connected to C1 and C1 connected to C2. That is a way of applying duplication. First you break pi bond and carbon atoms are connecting like this, C2 connected to C1 and C1 connected to C2. For example, now C double bond O is there, C double bond O. So how we are applying duplication? Now here carbon oxygen, we have one sigma bond and one pi bond, and what we are breaking here, just you break pi bond but not sigma bond. After breaking of pi bond, oxygen connected to carbon and carbon connected to oxygen. That is the duplication process. For example, here CH double bond NH given, same group, just you write like this, CH double bond NH. These two are directly connecting through double bond. Carbon and nitrogen directly connecting through double bond. Okay, and we have one sigma bond and one pi bond. How we are applying duplication? Here NH. Directly connected atoms are only carbon and nitrogen. These two atoms are connecting through the double bond. Okay, right. So if you want to apply duplication, first you break pi bond, and after breaking of pi bond, nitrogen connected to carbon and carbon connected to nitrogen. That's it. So that is a way of applying duplication process. So first point here, so where we are applying duplication? Duplication we are applying on double bonded systems. Just you break the pi bond and connect the atoms like this. Next one, for example, triple bonded systems are given like this: C triple bond C, C triple bond C. Here we are applying triplication. So first point, here we have how many pi bonds? Two pi bonds are there. For example, if you break pi bond, one pi bond, then connect carbon and carbon. After breaking up second pi bond, again connect carbon and carbon. Okay, that is the way of applying triplication. In case of triplication, we are breaking two pi bonds. For example, C triple bond N is given. C triple bond N. How we are applying triplication? Now we have one sigma bond and two pi bond. For example, if you break one pi bond, then nitrogen connected to carbon and carbon connected to nitrogen. For example, if you are breaking second pi bond, again one more time, nitrogen connected to carbon and carbon connected to nitrogen. So that is the way of applying triplication. So duplication we are applying on double bonded systems, triplication we are applying on triple bonded systems. And sometimes in some books they are writing like this: after applying duplication and triplication, they are writing like this: 0, 0 and 0. Here also same thing, 3 zeros. What is the meaning of these 3 zeros? 3 zeros are known as phantom numbers. So it indicates that after writing these phantom numbers inside the bracket, it indicates that beyond beyond the carbon beyond the carbon there is no further connectivity. There is no further connectivity. That is the meaning of phantom numbers. Okay. For example, if you want to move in this direction, finally you are going to stop at this carbon atom. Here also same thing, we are stopping at this carbon atom. Beyond that carbon atom, there is no connectivity. That is the meaning of phantom numbers. That is the story about duplication and triplication. Okay. Next one. Now according to RS rules, yeah, already 2 points are what completed. First we are starting with atomic number. So higher atomic number getting higher priority and lower atomic number getting what? Lower priority. Okay. For example, atomic numbers are same. Then we go for mass numbers to get the first point of difference, right? For example, some cases, if there is a competition between cis and trans, and sometimes there is a competition between Z and E, okay, and sometimes there is a competition between RS, next one RR, next one SR, next RR and RS, next one SS, RS, SS, SR, and competition between RR and SS. So where we observe this kind of situations. Now we will now discuss in case of real molecules. For example, according to RS configuration, if there is a competition between cis and trans, high priority should be given to cis. Next one, between Z and E, high priority given to Z. For example, if there is a Z and E, first priority given to Z and second priority given to E, something like that. Okay. Now Z getting higher priority than E. For example, if there is a R and S, R getting higher priority than S. For example, if there are RR and SR, RR higher priority, RR RS, SS RS, SS SR. For example, between RR and SS, RR getting higher priority. Okay. Now these are the priorities on the basis of CIP rules. Right. Next one, we are giving RS configuration on wedge projections. RS on wedge projections. RS on wedge projections. Okay. So how we are providing RS configuration on wedge projections? First point, here I am going to take like this. Now here two are in plane, and here one bond is back of plane and one bond is front of plane, or above the plane and below the plane. So this is the wedge representation I am taking, right? First important point here, around the carbon atom. For example, here this is the carbon atom. Around the carbon atom, four different groups are there: P, Q, R, and S. Four groups are there. We are giving priorities 1, 2, 3, 4 on the basis of CIP rules. Okay. After giving priorities, one second. After giving priorities, for example, first priority, second priority, third priority, and fourth priority. Okay, 1, 2, 3, 4 priorities are there. So after giving 1, 2, 3, 4 priorities according to CIP rules, right? For some time you forget about the fourth priority, or first you look at this fourth priority where it is connected. It is nearer to observer or away from the observer, away from the observer, away from the observer. And second one I am taking now here, that fourth priority same connected to away from the observer, but in case of remaining priorities are like this. So 1, 2, 3 I am taking anti-clockwise direction, but here I am taking in clockwise direction, like 1, 2 and 3. Just you observe these two wedge projections. Okay. First point, how we are providing 1, 2, 3, 4 priorities. 1, 2, 3, 4 priorities are provided on the basis of CIP rules. Okay, right. Next one, after giving 1, 2, 3, 4 priorities, first one, if your least priority group is present on broken wedge. Broken wedge nothing but nearer to observer or away from the observer, away from the observer. Here also same thing. Now that fourth priority connected to away from the observer, away from the observer. In both the cases, your least priority group, fourth is the least priority, one is the higher priority. Okay, your least priority group is present on broken wedge or away from the observer. In that case, now you start from 1, 2 and 3. We are moving along 1, 2, 3, and here we are moving along 1, 2, 3, 1, 2, again 3, 1, 2, 3. What is the priority direction? 1, 2, 3 priority direction. 1, 2, 3 is present in clockwise direction or anti-clockwise direction. Anti-clockwise direction. Then yes configuration. And here we are moving in clockwise direction. Clockwise direction or configuration. Okay, that is the way of giving RS configuration, right? But what is the condition here? Whenever you are giving RS configuration on wedge projections, first important condition, you look at towards the fourth priority. If your fourth priority is broken wedge, fourth priority present on broken wedge or away from the observer, then after that we are looking towards 1, 2, 3 priorities. If 1, 2, 3 priorities are in clockwise direction, R configuration. 1, 2, 3 priorities in anti-clockwise direction, S configuration. Okay, right. Now that is a very important point. Fourth priority should be on wedge. Should be on wedge. This is the important point. Either broken wedge or thick wedge, no problem. But what is the condition? Fourth priority should be on the wedge. Now come to next example. Now here again I am taking broken wedge and thick wedge. Broken wedge and thick wedge. Now here I am taking fourth priority on the thick wedge. Here also I am taking fourth priority on the thick wedge. Next one, 1, 2, 3 priorities I am taking like this. Now first priority, second priority and third priority. Here first priority, second priority and third priority. For example, this is the situation. Okay. Now this is the condition. What about the fourth priority? Fourth priority should be on the wedge. That may be broken wedge or thick wedge, no problem. But straight away, if it is present on the broken wedge and on the basis of direction of 1, 2, 3 priorities, if 1, 2, 3 priorities are in clockwise direction, then what is the configuration? R configuration. If 1, 2, 3 priorities are in anti-clockwise direction, S configuration. But in this one, no problem, your least priority group is present on wedge, but thick wedge. Here what is the direction? Anti-clockwise direction is there. 1, 2, 3. and here 1, 2, 3 are in which direction? Clockwise direction or anti-clockwise direction? Clockwise direction. Okay. Now, if your least priority group is present on thick wedge and the direction is anti-clockwise direction, what is the expected configuration? Yes configuration. But here configuration is reversed. Now our configuration should be what? R configuration. That is a very important point. Okay. Now we are taking opposite configuration, reverse configuration. Here clockwise direction or anti-clockwise direction? Clockwise direction. Clockwise direction, but least priority group is present on thick wedge. We are expecting R configuration, but what is the actual configuration? S configuration. Why? Because now very simple thing, according to that RS configuration, least priority group should be on the broken wedge. Least priority group should be on the broken wedge, and after that 1, 2, 3 priorities are in clockwise direction, R configuration. Next 1, 2, 3 priorities are in anti-clockwise direction, S configuration. But here your least priority group is present on thick wedge. That's why we are taking opposite configuration. You can also solve problem like this. Now, for example, same here broken wedge, next one thick wedge. For example, this is the least priority, and here 1, 2 and 3 priorities are there. According to this first rule, now come to this one. If your least priority group is present on broken wedge, then according to 1, 2, 3 priorities, if they are in clockwise direction, R configuration, anti-clockwise direction, S configuration. Now, in order to bring fourth priority onto the broken wedge, we can do like this. You can exchange priorities like this. Now that is what we call even exchange. Two groups we are exchanging. Now then what is the result here? Broken wedge and thick wedge. If these two are exchanging, here you are getting 3, next one here 4. Like that exchange 1 and 2 also. Here 1, next to 2. Then what is the position of your least priority group? Your least priority group is present on broken wedge. Then no problem. 1, 2, 3. Clockwise direction or anti-clockwise direction? Anti-clockwise direction. Then what is the configuration? Yes configuration. You can also do like this. Otherwise, now simply if your least priority group is present on thick wedge, if it is in anti-clockwise direction, take R configuration, and if it is in clockwise direction, we are taking S configuration. Okay. Now these are the rules on wedge projection. Let us start first example here. Very simple example. For example, here fluorine. Otherwise, here I am taking that fluorine, chlorine, bromine, and iodine. What is the RS configuration for the given molecule? So what is the RS configuration and wedge projection? Now here, for giving RS configuration, first you look at the connected atoms. This is iodine. Okay. One second. Iodine, right. So how we are giving priorities? First you look at iodine, bromine, chlorine and fluorine. So which one has higher atomic number? Iodine. First priority should be given to what? Iodine. Next priority given to bromine. Next third priority. Next fourth priority. First you look at fourth priority. What is the position of your fourth priority? Your fourth priority present on the broken wedge. That's why no problem. There is no need to go for any kind of exchange. Okay. Next one, we are looking towards 1, 2, 3. So 1, 2 and 3. What is the direction? Clockwise direction or anti-clockwise direction? Anti-clockwise direction. Then what is the configuration? Yes configuration. Okay, right. For example, same molecule given like this. Here iodine, next one bromine, next one here fluorine given, and here chlorine given. So how we are giving RS configuration for the given molecule? Same thing, first priority should be given to what? Iodine, second priority bromine, third priority chlorine and fourth priority fluorine. After giving 1, 2, 3, 4 priorities, first you look at fourth priority. What is the position of your fourth priority? That is present on broken wedge or thick wedge. That is present on broken wedge. Now here you can solve like this. What is the priority direction of 1, 2, 3? Clockwise direction or anti-clockwise direction? Anti-clockwise direction. And your least priority group is present on thick wedge, that is nearer to observer. Then what is the configuration? S configuration or R configuration? Anti-clockwise direction, but configuration should be what? R configuration. For example, if you want to solve like this, here also you are getting same configuration, bromine, and here chlorine and fluorine given. Let us try to exchange atoms like this. Yeah, these two, iodine and bromine, even exchange. And again fluorine and chlorine and fluorine. Okay, we are exchanging like this. Then what are the priorities? First priority, second priority, third priority and fourth priority. We are trying to bring fourth priority onto the broken wedge. Okay, you can also do like this. Otherwise, if fourth priority present on thick wedge, if it is in clockwise direction, S configuration, anti-clockwise direction, R configuration. Okay, now here after even exchange, now I am writing the same point. After even exchange, after even exchange, this is the situation. And what is the priority direction? 1, 2, 3, clockwise direction. Then what is the configuration? R configuration. Same or different? You are getting same configuration. Okay, so that is the way of giving RS configuration on wedge projections, right? Let me give one more molecule. Now this is our molecule. Here there is a OH and hydrogen. One second, I am going to take hydrogen here. Otherwise, one second, for least priority here let CH3 and C2H5. For better understanding, here I am taking C2H5 and hydrogen. Now do this molecule. First of all, this is our asymmetric center. 4 different groups are there. Okay, right. How we are giving priorities? Now clearly I am writing like this. Same molecule. Here this is my carbon atom, hydrogen, and broken wedge CH2, hydrogen, and hydrogen. And here carbon, hydrogen, and hydrogen. Next one here OH is given. How we are providing 1, 2, 3, 4 priorities? 1, 2, 3, 4 priorities we are providing on the basis of an atomic number. What is the first connectivity here? Oxygen. Here first connectivity carbon. Again first connectivity carbon. Here what is the first connectivity? Hydrogen. First of all, on the basis of atomic number, now we can give priorities like this. First priority should be given to what? OH. First priority should be given to OH. There is no confusion of giving first priority and also fourth priority. Now fourth priority should be given to what? Hydrogen atom. Okay, right. Next one, here carbon atoms are same. First connectivity same or different? Yes, first connectivity same. Then go for second connectivity. What is the second connectivity here? Hydrogen. You can take hydrogen, and hydrogen. But here what is the second connectivity? Now simply I am writing like this. First connectivity, first connectivity point of view, carbon and carbon. And what about second connectivity? Second connectivity here hydrogen, and hydrogen. What is second connectivity here? Hydrogen, carbon. Same thing I am writing like this, carbon, hydrogen and hydrogen. Now you compare between these two, hydrogen and carbon. Which one getting higher atomic number? Carbon higher atomic number when compared to what? Hydrogen. That's why high priority given to this one when compared to methyl. 1, next one, 2, 3 and 4. These are the priorities. First priority second priority, third priority, and fourth priority. Okay, 1, 2, 3, 4 priorities. But according to wedge, now what is the position of least priority group? Least priority group should be present on the wedge. That may be thick wedge or broken wedge. Okay. Now just in order to bring that fourth priority onto the wedge, I am doing like this. Just I am trying to exchange these two. So once again I am writing, yes, this is my first priority, second priority, third priority, and fourth priority. Okay. So before going to give RS configuration, just you try to exchange these groups. Why we are exchanging or even exchange? Why we are doing even exchange? Just in order to bring fourth priority onto the broken wedge. Okay. Then what is the situation here? After exchange, after exchange, here what is the priority? Fourth priority. Next one here, second priority. If you are exchanging these two, third priority and here first priority. Now there is no problem. Why? Because our fourth priority is present on the broken wedge. Then you look at priority direction. 1, 2, 3. What is the priority direction? Anti-clockwise direction. Then what is the configuration? Yes, configuration. Okay. So that is the way of giving RS configuration. Next one, I am giving molecules like this now with here it is OH. Next one here also OH. What is the RS configuration at these carbon atoms? Both are above the plane given. That is the given molecule. So how we are giving RS configuration? First of all, once again I am going to take same molecule here. OH is given. Next one OH is given. Okay. By default, even though they are not giving now fourth priority, what is the fourth priority here? By default, fourth priority should be what? Hydrogen. Next one here also, what is the fourth priority? Hydrogen. Okay, right. Now these are the asymmetric centers. Okay. Now how to assign RS configuration? First you start from this carbon atom, right? What is the first connectivity? Oxygen. Next one here, carbon. Here also carbon. Once first connectivity is same, then go for second connectivity, forgetting first point of difference. Here further carbon connected toward oxygen atom. That's why first priority given to this one, second priority, third priority and fourth priority. That is the priority direction. First of all, we are looking towards fourth priority. What is the location of your fourth priority? Fourth priority present on broken wedge. That's why no problem and there is no need to go for even exchange. And we are looking towards 1, 2, 3 priorities. 1, 2 and 3. What is the priority direction? Clockwise direction. Then what is the configuration? R configuration. Okay, fine. Next one, first priority should be given to OH and here second priority, third priority and hydrogen fourth priority. What is the priority direction? Priority direction, clockwise direction. And what is the position of your least priority group? Broken wedge. Then what is the configuration? R configuration. So here also R configuration. So very important. Here clockwise direction, next one here also clockwise direction. In both the cases we are getting R configuration. Okay, right. Next important example. Here broken wedge, something like thick wedge is given, right? Here I am taking COO minus and here COOH. Next one NH3 plus and here NH2. What is the RS configuration? What is RS configuration of this given molecule? Very good example. Now clearly I am taking like this: nitrogen, hydrogen, hydrogen and hydrogen, positive charge. Next one here nitrogen, hydrogen and hydrogen. next which is given here C double bond O minus, next on thick wedge C double bond OH, right? So how we are giving priorities? Now first we are going for first connectivity, nitrogen, nitrogen, carbon and carbon. So which one has higher atomic number? Nitrogen atomic number is more when compared to carbon. So first complete priorities of these two, nitrogen, nitrogen, same or different? They are same. Then go for next connectivity, hydrogen, hydrogen and hydrogen. But here how many hydrogen atoms present? Two hydrogen atoms are there. But here three hydrogen atoms. One extra hydrogen atom is present. That's why first priority given to this one and here second priority. Next one, in these two groups, this part is exactly same. But here extra hydrogen atom is present. So first priority, second priority. Next one here, third priority and fourth priority. So before going to give RS, first we are looking towards fourth priority, least priority present on broken beds. That is away from the observer. That's why no problem. Then 1, 2, 3 priorities. What is the priority direction? Clockwise direction or anti-clockwise direction? Anti-clockwise direction. What is the configuration? Yes, configuration. Okay. Now these are the some important examples on RS configuration by using wedge projections, and few more molecules are there like epoxides and cyclohexane ring system. So this kind of examples and Fisher projections are there. Okay, these examples we will discuss in the next class. Okay, thank you.